The energy required to break the OH bond in the OH molecule is 7.45 times 10 to the negative 19 joules. There should probably be a negative sign here because that's an OH minus molecule. We need to calculate the longest wavelength in nanometers of radiation required to break the OH bond in one OH molecule. Okay, so the hydroxide molecule. Well, we're told that the energy required to break it, so we're just going to say that E is equal to 7.45 times 10 to the negative 19 joules. That's the energy that's required. We also know that E is equal to hc over lambda. So h is our Planck's constant, c is the speed of light, and lambda is the wavelength. So now what we need to find out, and that's what we're looking for, right? The wavelength. We want to know what wavelength we have. So if we rearrange this equation, we'll find that lambda is equal to hc over the energy. Okay. So when we plug this formula in, Planck's constant is 6.626 times 10 to the negative 34 joule seconds. Okay, we're going to multiply by the speed of light. That's 2.998 times 10 to the 8 meters seconds to the negative 1. And we're going to divide by the energy that we were given here. So that's 7.45 10 to the negative 19 joules. Okay, before I actually do this calculation, I'm going to look and see that my units cancel. So joules cancel with joules. Seconds to the negative 1 cancels with seconds, and I'll be left with something in meters. Well, that's fine. I'm going to have to do some conversion because the question is asking me for it in nanometers. That's all right. So to begin with, we'll just solve this, and we get 2.56 times 10 to the negative 7 meters. Okay. Well, all I have to do for this is just multiply that by my conversion from meters to nanometers, and I'll end up getting 2.56 10 to the negative 7 times 10 to the 9 nanometers per meter. This is meters, and my meters cancel out, and I'm going to get 256 nanometers, and that's my answer. If I look at the electromagnetic spectrum, just to see where this falls, 256 nanometers is going to be less than, it's going to be in the ultraviolet region of the spectrum. So that's a pretty high energy wavelength. The second question here says, does a photon with frequency of 5.00 times 10 to the 14 per seconds have sufficient energy to break the OH bond in the OH molecule? Want to justify our answers with calculation. We can't just say yes or no. So what we have to do then is we have to convert this frequency into a wavelength and see if it's going to have this much energy, right? We actually could just solve for the energy rather than converting to the wavelength comparing to this. Why don't we just do that since we have the energy here? Okay, so the energy is equal to hc over lambda, or it's also equal to h times the frequency. Okay, so let's just do it this way. It's a little easier calculation rather than doing all of that up there. This is going to be 6.626 times 10 to the negative 34 joules seconds. Multiply that by the frequency. The frequency is 5.00 10 to the 14 seconds to the negative 1. And so we see that our seconds cancel, and we're left in unit of joules. The answer to this is 3.31 10 to the negative 19 joules. Now, so this is how much energy one photon has with this frequency, and we can tell that that's actually smaller. So this is going to be smaller than the 7.45 10 to the negative 19 joules that we need. So that means that no, this does not have enough energy to break that bond.